Welcome back. Today we are diving into one of the tools used in electrical measurements, potentiometer. In this video, we learn how this device works, how it can measure EMF, compare EMF of two different cells, and even determine the internal resistance of a cell. First off, let's see what a potentiometer is. You now know how to measure EMF of a source or potential difference across a circuit element using a voltmeter. An ideal voltmeter should have finite resistance so that it does not draw any current when connected across a source of EMF. Practically, it is not possible to manufacture a voltmeter which will not draw any current. To overcome this difficulty, we use a potentiometer which draws no current from it. Here is the setup. A and B are the ends of the wire. K is the jockey that slides along the wire. S is the scale that helps us measure the position of the jockey, and jockey slides over the rod CD. Potentiometer consists of a wooden board on which a number of resistance wire, usually 10, of uniform cross-sectional area are stretched parallel to each other. The wire is of manganese or nichrome. These wires are joined in series by thick copper strips. In this way, these wires together act as a single wire of length equal to the sum of length of all the wires. The end terminals of the wires are provided with connecting screws. Here, A and B are the ends. A meter scale is fixed on the wooden board parallel to the wires. A jockey is used to make a sliding contact on the wire, and this is where the magic happens. It makes a knife edge contact at any desired point on a wire. Jockey has a pointer which moves over the scale. It determines the position of the edge contact. Let's measure EMF of the cell using potentiometer. Consider a steady source E as EMF connected across the uniform wire AB of length L. Say steady current I flows through the wire. The potential difference across AB VAB is equal to RI. Now, if R is the resistance per unit length of the wire, K is the potential drop across the unit length of wire, then the resistance of the wire is R into L. Since resistance per unit length into the length of the wire, potential drop of the wire is KL. So, if you consider the length L1 till this point, then the potential drop will be, let's denote it by V1, K times L1, which is equal to E by L into L1. We'll need this later. Thus, the potential falls linearly with distance along the wire from the positive to the negative end. Now, we need to measure this unknown voltage V. The positive terminal of the cell is connected to end A, and the negative terminal is connected through the galvanometer to the jockey, which has variable contact. The jockey can be moved. Here, note that if V is greater than E, we can't find the null point in the galvanometer. We are considering E to be greater than V. We insert the key K1 and begin moving the jockey from point A towards point B. As we move the jockey, we are looking for the point where the potential drop across the segment. Suppose this is, we arrive at a point here. The potential drop across AY should be equal to the potential drop across the voltage V. That's what, at this state, the galvanometer shows no deflection and we achieve the point, null point. Let's find the null point here. Let's say the jockey is initially at point Y dash. The potential drop across the length AY is still less than this voltage. This causes the current due to the V to be higher than the current caused by the potential drop across Y dash, resulting in a deflection in the galvanometer. As we continue the jockey, we find another position Y dash where the potential drop across the wire A Y dash exceeds that of this voltage. In this case, the galvanometer shows a deflection in the opposite direction. Now we move the jockey slowly back to the position between that of Y and Y dash, adjusting carefully until we reach a point, say Y, where the potential drop across AY is exactly equal to this unknown voltage V. This is at null point. At this point, the length of this wire AY is L1. V is equal to K times L1, which is equal to E by L into L1. Thus, the unknown voltage V is measured when no current is drawn. What are the advantages of using a potentiometer? When the potentiometer is balanced, no current is drawn from the circuit on which the measurement is being made. It produces no change in the conditions in the circuit to which it is connected. It makes use of Null method for the measurement, and the galvanometer used need not be calibrated. Let's extend the potentiometer technique to compare the electromotive forces or e.m.f. of two different cells. Let's say Daniel cell and Lecland cell as examples to demonstrate how we can accurately compare their EMFs. We have two cells here, E1 and E2. The potentiometer wire will be used to measure the balance points for both the cells. The cell with EMF E1 is connected through the terminals 1 and 3 of key K1, while the second cell with EMF E2 is connected through the terminals 2 to 3 of key 2. Initially, we'll consider this as the setup. The cell E1 is connected. We move the jockey along the potentiometer wire until we find the balance point. This is the point where the potential drop along the wire, say AY1, matches the E1, EM of the cell. So E1 is equal to potential drop across AY1. Now we connect the cell E2. This part is connected. And repeat the process to find the balance point. The jockey is moved along the wire A to B, and we find a new balance point, say Y2, with the length from A to Y2 being L2. Just like for cell E1, at this balance point, the potential drop across the length L2 of the wire equals the EMF of the cell. Now let's apply the potentiometer principle. For the cell E1, the relationship between its EMF and the length L1 is given by E1 is equal to K times L1, where K is the potential gradient of the wire. For the cell E2, similarly, it's K times L2. We can write this as K is equal to E1 by L1. From this, K equal to E2 by L2. Therefore, E1 by L1 is equal to E2 by. From this equation, we express the ratio of EMFs as E1 by E2 is equal to L1 by L2. This equation tells us that the ratio of EMF of two cells is equal to the ratio of length at which the balance point was found. With this method, we can compare the EMF of two cells using the potentiometer. One more application of potentiometer is measuring the internal resistance of a cell. Here is how. The figure shows the circuit diagram for measuring the internal resistance R of a cell of EMF E1. Resistance box R with the key K1 is connected in parallel with the cell. Primary circuit, that is, this is the primary circuit, has a standard cell, a rheostat, and a one-way key. as soon as the K key is closed, a current I begins to flow through the wire AB. The key K1, this is kept open. And on moving the jockey, balance point is obtained with the cell E1. That is, here the balance point is obtained. Say Y1. A Y1B L1. L1. Then we can write E1 is equal to K times L1. Key K1 is closed. This introduces a resistance across the cell. A current, say I1, will flow in the loop E1 or K1 E1. So through this the current I1 flows. This is due to the cell E. Using Ohm's law, we can write I1 is equal to E1 by R plus R. What is this R? This is the internal resistance of the cell. What does this mean? This means that the potential difference V1 of the cell will be less than that of the E1 by an amount I1R. So the value of V1 is equal to I1 times potential difference across this. E1 by R plus R. The potential difference V1 is balanced on the potentiometer wire without change in current I. So the balance point be the Y2 such that A Y2B L2. So here V1 is equal to K times L2. These equations, this one and this one. E1 by V1 is equal to K times L1 by K times L2. From this we can write E1 by V1 is equal to R plus R by R. So equating these two, R times L2 plus R times, we need small r, which is equal to R into L1 minus L2 divided by L2. Thus, by knowing the value of R, L1 and L2, we can obtain the value of internal resistance of the cell. Let us see an example. The length of the potentiometer wire is 5 meter. It is connected to a battery of fixed e.m.f. Null point is obtained for the Daniell cell at 100 centimeter, which is 1 meter. If the length of the wire is kept 7 meter, what will be the position of the null point? Let us say the e.m.f of the battery be E. The potential gradient initially for the length of 5 meter is K is equal to E by L, which is equal to E by 5. When the length of the potentiometer wire is 7 meter, then the potential gradient K2 will become E by 7. Initially, the null point is obtained for the Daniell cell of with potentiometer 5 meter. We obtain it at for the length of 1 meter. So we can write E is equal to E by 5 into 1, which is equal to E by 5. And for the length, this is for L1. For L2, K times L into L2. These are both same cell, so we can equating these two, we get E by 5 is equal to E by 7 into L2. Therefore, L2 is equal to 7 by 5 which is equal to 1.4 meter. To recap, potentiometer is a device used for measuring voltages without drawing the current using the formula V is equal to KL1 or is equal to EL1 by L. It is also used in comparing the EMFs of two different cells using the formula E1 by E2 is equal to L1 by L2. And also it is used in determining the internal resistance of a cell R is equal to capital R into L1 by L2 minus 1. Thanks for watching. If you found this video helpful, don't forget to like, share and subscribe for more such videos. And if you have any questions or topics you'd like me to cover, leave them in the comments below. I'll see you in the next video.